valence electrons are your electrons in the outermost energy level. And I mean here major, and I didn't write that down, I should have. Outermost major or principal energy level. And some people, of course, call that shell. And this term is usually used only for the A families. It's not a very useful term for the B families or for that last two rows, the lanthanides and the actinides down at the bottom. So, why is this so important? And that was, I think, a test question or a review question. Where are the important electrons? The outermost shell, major shell, because that's what's in contact with the rest of the world. So, if you're going to lose electrons, it will be from the outermost shell, because that's what's out there touching other stuff. Okay, or if you gain electrons, that's where they go, or if you shed electrons, that's where the action is. So we call those the valence electrons. Okay, if we look up there, and this reviews the electron configurations just great. So if we come up here, let's say I take sodium. What if I ask the question now, how many valence electrons? In the past, what I used to ask you is, sodium, what's it going to do? Lose or gain electrons? And you all, of course, always said lose. And I would say how many? One. And if it lost one, then it's isoelectronic with what? Neon. Okay, and there's this tremendous drive towards stability. What's stability? Having a fine number of electrons. Okay, now I'm going to ask the question just a little bit differently, but it's info you know. For sodium, if we did do the electron configuration, we would say neon core, and then what would we say? 3s1. So it has one valence electron. If we did potassium, what's its core? Argon core, and then we would say 4s1. So how many valence? 1. Guess what? That's true of that whole family. So everybody in the 1A family has one valence. If we move to the 2A, if we did calcium, okay, what's your core for calcium? Argon core again, and then what would we say? 4s2. So how many valence? 2. Take a wild guess. How many does barium have? Valence? 2. 2A family has 2 valence. Now, it gets a little trickier here because I've got to emphasize we mean major shell, not sublevel. So if I go to boron and I say, how many valence electrons, what would you tell me? 3. Because it's major shell. Because if you're doing boron electron configuration, you would be saying helium core, then you would say 2s2, 2p1 for a total of 3. So all these guys have 3 valence electrons. Do you see a wonderful clue? The family name. Okay, so how many valence does the 4A have? 4. 5, 6, 7, and 8, except for helium. And how many valence would helium have? 2. Fantastic. So that's a term. Now, what we're going to look at in this chapter are 2 types of bonding. Let's go back and let's talk. In chapter 1, there was a chart or a diagram about halfway through the chapter, and it had matter up at the top, and then we split and we said we had mixtures here and we had pure substances here. Okay, when they talk mixtures, remember it's a little of this, a little of that, no definite ratio, and there were 2 types. What are the 2 types? What's one, Charles? Mixture. We got 2 types of mixtures. Heterogeneous, and Liz, what's the other? Homogeneous, okay. And of course, when we work with solutions, at the end of chapter 3, solutions are always what kind of mixtures? Homogeneous mixtures, think of salt and water. Okay, now let's go over to the side we're talking about now. Pure substances, there's 2 kinds. Marco, can you tell me one? Compounds. And the other, Meredith? You got pure substances, compounds, or? Elements, exactly. Okay, compounds. the definition back then was 2 or more elements have gone together in a definite ratio, and we usually can't separate them by ordinary physical means, meaning filtration, decanting, that kind of stuff. Okay, probably all of you have table salt at home, sodium chloride. And I bet not one of you has ever worried about, you're going to come home this afternoon and the sodium chloride will have decomposed and you have dangerous, explosive sodium metal in your kitchen and toxic chlorine gas in your kitchen. I know you worry about a lot of things, but I bet that's not on the list. So the question is, what holds the sodium together with the chlorine? What bonds them? Okay, and that's what we're going to be talking about today, the bonding in compounds. And there's 2 major types that we're going to talk about. One is ionic and one is covalent. Okay, if you look at the outline of chapter 7, and this is not all of it, but it's the bulk of it. In fact, in this chapter, this is probably the most important section of all, this number 5, and I hope we'll get down into that really well, because once we get there, we've broken the back of this chapter. So, if you look at it though, section 2 is about ionic bonding, and the rest of the chapter is about covalent. So for us, we're going to spend 90% of our time thinking about the covalent type. Okay, so let us, first of all, for section 1, we're going to learn to write Lewis dot structures for elements, neutral elements. And then down here in section 5, we're going to learn how to do Lewis dot structures for compounds. So be sure you separate the 2 in your mind. So first, here's how we do it. I have a sodium atom, not an ion.
This is the Lewis dots.
Yeah, we're talking Lewis dots here. We're in section 1. Okay, every electron is represented with a dot, but only the electrons in the valence shell, because that's where the action is. So if I have a sodium, how many valence electrons does it have? 1. So we put 1 dot. That's its Lewis dot structure. It's a visual to show you it's got 1 valence electron, which is going to be helpful for us because if you know about valence electrons, you can predict probably what's going to happen. Now, you've already learned an alternative technique just using the periodic table. So now this is a visual, drawing pictures of it. So I don't care where you put it. What we do is we use the right side, the left side, the top, and the bottom. We don't use the corners. And the maximum number of electrons on a side will be 2. Now, if I go to calcium, how many valence electrons does calcium have, Hina? 2. So we could draw it. Now, some people will draw it like that. Or sometimes people will do it like that. And I really don't care which you do. But just recognize it's the number of dots that count, and their position to me is not important. Let's go on. What if I have phosphorus? Okay, look up there where phosphorus is. Emily, how many valence electrons does it have? 5. So here's what I do, and this is just habit. I go 1, 2, 3, 4, 5. Okay? But it's my own habit. I start here on the right side and I move around it. But the point is, the count is what's important. So I glance at that and I see, it's got 5 valence electrons. And later on in this chapter, in fact, real soon, we'll start talking about the octet rule. In fact, I don't think I have it written here. It must be further down than this, but it's important to hear it up front. Octet, of course, means 8, just like in music. An octet means 8. Okay, the octet rule is most things, not 100%, but the majority of elements would like to have 8 electrons in their outermost shell. So this is a great visual how how many more does this guy need? You can see it's got 1, 2, 3 vacancies. But now remember, it's an alternative to looking up there because you already knew it by position on the periodic table because we hit that so hard back in chapter 1 or 2. So this is just an alternative. Okay, is everybody okay on doing Lewis dots of anybody from an A family? Okay, the reason we do not do the B families, because the term valence electron technically means outermost shell. Okay, if we did titanium down here in the B families, let's think about electron configuration. Who would be the core? Argon. Then we would say what? 4s2, 3d2. Okay, what's the outermost shell? The fourth. Okay, but with these guys, that 4, the 4s's, can get in on the action, but so can the 3d's. Because titanium can be +3. It can be weird. And so the term valence electron doesn't really work for those guys. But it works beautifully for the A families. So that is section 1. Let's get into ionic bonding for this brief time. And let me show you an equation. And it's just a way of looking at it. It's not a necessary way of looking at it because there's other ways of understanding it. Okay, I have a sodium. Tell me what a sodium tends to do. Gain or lose electrons? Lose. When it loses that electron, what charge does it take on? +1. And I show it like that. And I think I had this up on the board for you once before. And I also, when I had it up here before, I said, this is sometimes written like this. You may have seen it like this before, but I don't like it. And here's why I don't like it. Technically, it is correct, because the arrow is just like an equal sign in algebra. So if it's plus something over here, if I moved it across the equal sign, then it's minus that. I do not like this because I like to show the electron is a product that somebody else gets to use. And I don't think that's as clear if you write it like this. So I'm going to take that out of there. Now, I have chlorine. I have chlorine here. When you look up there for the number of valence, Brittany, what would you tell me? Can you spot? 7. So I would put 1, 2, 3, 4, 5, 6, 7. Now, Nicole, what's this chlorine going to tend to do? Gain 1. And there's 2 ways to look at that. I saw Nicole looking at the periodic table, because you're most familiar with that. You say, hey, if it gained 1, it'd be isoelectronic with argon. But here, you got a vacancy if you think octet rule. And if it gains 1, then it's Lewis dot structure. Looks like that. It's got the full 8. What charge is it, Bruce?
Positive.
If it gains 1?
Oh, negative.
Negative. Look at this. We got the perfect marriage. This guy is a giver. This guy is a taker. In fact, let's see, whoops, I don't want to put this. That's one and the same electron. And so what do we have? The sodium becomes +1 because it wants to unload an electron. The chloride wants to gain. Now notice something about Lewis dots. If you start out and you have 1 valence and you lose it, then technically you really have over here an octet, but they don't show it. You start out with, what were you? And then if you lose it, they don't say, okay, now it's isoelectronic with neon and it's got an octet again. It's just not shown by custom. So this guy loses and becomes +1. This guy gains and becomes -1. They're going to be hugely attracted to each other because opposite charges attract. And of course, more charge, more attraction. If they've been +2 and -2, even stronger. But we have the perfect marriage, and we just made sodium chloride. And we come over here, this is referred to as an ionic bond, because ionic bonds are defined as when you have a complete transfer of electrons. Complete transfer of electrons. And here's how we speak. Sodium chloride. And of course, when we actually write the formula, I don't show the charges. Remember how that's just the rough draft? This is how we show it, that we say, what kind of a bond does it have? We say ionic. You also are asked, what kind of compound is it? It's ionic. So we call the bond ionic, we call their compound ionic. Okay, so one's a giver, one's a taker, think ionic.